Hello everyone. Complex number is an important tool to analyze an AC RLC circuit. In this unit, we will define phasor as a type of vector. Complex numbers can be associated with this phasor in the same way. It is important to understand that a phasor diagram is a mathematical model of a circuit. The phasor simplifies the mathematics by showing certain resultant in terms of vector. Before I get into the details how to calculate the inductive reactance, the capacitive reactance, and the impedance, I would like to draw your attention to the circuit right here. As you see, this circuit, I have an AC source. I connect in the circuit a resistor, an inductor, and a capacitor. So it is an AC series RLC circuit. Note that the current is the same throughout the entire circuit, and also the diagram indicates that I am connecting the resistor, the inductor, and the capacitor in series. So mathematicians would like to translate this circuit into a mathematical model, or it's called the phasor diagrams. And the phasor diagram for this AC RLC circuits connected in series is presented below. Okay, as you can see, it is a complex plane, right? So complex plane consists of the imaginary axis, the vertical imaginary axis, and the horizontal real axis. So we are going to concentrate on the positive part of this imaginary axis, which is the positive J, and we also concentrate on the negative part of this imaginary axis, which is the negative J, and also the positive part of the real part of this complex plane. Note that we are not talking about any negative part of this real axis. The reason for that is the real axis associated with your resistor. The resistor is a real value anyway. You pick up a resistor right from your toolbox and it has a positive value all the time. You cannot pick a resistor and having it as a negative value. Alright, so the real part of this complex number associates very closely with your resistor in this case. And the impedance is the resultant vector between the real part and your inductor and your capacitor. Before I explain further into this diagram, I would like to go back and let's review the concept of a DC circuit and an AC circuit, how the frequency affect the current in this case. Okay, so when the frequency is equal to 0, and we are talking about a DC circuit, when the frequency is equal to 0, then the capacitor acts like an open circuit and the inductor acts as a short circuit. As the frequency increases, now we are talking about an AC source. The inductor causes the current to increasingly lag the voltage. This concept leads to the positive phase of the inductive circuit. Therefore, we are talking about the XL, which is the inductive reactance, will take on the positive part of J. The phase is negative for the capacitive circuit, which is the capacitive reactance will take on the negative part of J, since the current leads the voltage in this case. The resistor, which is the real value, maintains the same phase between the voltage across it and the current through it. So to calculate the inductive reactance, XL measured in ohms is equal to 2 times pi times frequency and time the value of the inductor. To calculate capacitive reactance, which is XC, measured in ohm in this case, will be equal to 1 divided by 2 times pi times the frequency times the capacitor. So let's review that with a circuit diagram. Okay, so I am having a AC source. On this AC source, I generate a frequency. Okay, so I connect with this, a resistor, and then an inductor in series with each other. So here's my R, here's my L. So the inductive reactance XL is measured as 2 times pi times F times the value of your inductors, or they call it in the inductance, measured in Henry. Okay, XL, after you calculate that, will be measured in ohms. So now, if I have an AC source, I connect this with a resistor, and I also connect that with a capacitor. So in this case, I have a series RC circuit. The frequency generated through the circuit will give me XC. To calculate XC, I will have a formula as 1 divided by 2 times pi times frequency times the value of your capacitor C. So again, it will be measured in ohms. Alright. Okay. If we are talking about the reactance alone, okay, so the reactance alone in this case would be represented by just X. Okay, to calculate X as the magnitude, then I will always take the XL, subtract the value of the XC. So keep this in mind. As magnitude, take the value of your XL, subtract the value of your XC. This reactance is very important in terms of complex number as imaginary. Okay, so let's get back to our diagram. Or the mathematical model for this series RLC circuit. Honestly, I love to use the terminology mathematical models because mathematicians create this concept so all the engineer can calculate the impedance or analyzing this AC RLC circuit. Alright, so you can see that on this diagram you are having XL takes on the positive part of J. The XC capacitive reactance takes on the negative part of J. Okay, and again, real part is your resistor. And how do I have Z as the real part, adding that with positive JXL, and I have a vector showing like this. Okay, so let's review the concept of vector. Okay, review the concept of vector or phasor diagram. So let's get back to this slide, and I would like to draw a vector and review the concept of a vector. So vectors is represented by a magnitude and a direction. So the vector will have a head. So this is the head of the vector. This is the tail of the vectors. So I want to call this as vector V1. Alright? Okay. So if I have another vector, V2, if I would like to add vector V1 with vector V2, I will have to take this vector V1 and I will place it on to this head of this vector. So I will take the tail of the first vector, I place it on the head of this vector. So I make sure that I have the same magnitude here. So there's I place the tail of the first vector onto the head of the second vectors. Okay, so the resultant vector V1 plus V2 in this case will be connecting from the tail of the second vector to the head of the first vector. So this one will be my V1 plus V2. Alright, okay, so let's get back to our mathematical model for the series RLC circuits. Alright, so if I pick this part, this vector right here, I pick this vector and I project it onto this part of the graph. I put it right there. Okay, so my resultant vector in this case, which is Z, the impedance Z is represented by connecting the tails of the first to the head of the second, and is equal to the real part adding the JXL. Okay, so I do the same thing for the lower part of this diagram. I will pick up this vector, right? I will place it to the head of the first. Okay, so my resultant vector for this negative part is to connect from the tail of the first to the head of the second. Therefore, the impedance in this case will be equal to the real part adding this negative part of J. Therefore, I will have subtract J times XC. Alright, okay, so let's go over a few calculations in this case. Alright, before I get into the real calculation for the Z or the impedance, let's get back to our theory up here. Alright, okay, the total effective resistance to the flow of the current by the combination of the elements in the circuit is called the impedance. The impedance Z also measured in ohms. Okay, so the impedance Z is defined in terms of complex number, or the resultant vectors, as I mentioned earlier, as Z equal to the real part plus the X times the J. So remember, we define that X or the reactance is equal to the inductive reactance subtract the capacitive reactance. Okay. Using Pythagorean theorem, you can see that Z will be equal to the square root of R squared plus Z squared. So let's get back to that diagram. So you see here is more like a right triangle, and Pythagorean theorem indicated that if I want to find the magnitude of this Z, I have to take the square root of R, adding the square root of the X squared. Alright? Okay. So to calculate the argument or the angle, I have to use these formulas, also using trigonometry. However, the complex number in polar form will simplify all of this process. You can use your calculator to convert from rectangular form to polar form for your impedance. Note that this is a rectangular form right here, where R is your real part and where your XJ is your imaginary part. Okay? Reading the real part and the imaginary part, key them into your calculator, you can easily convert this impedance into polar form, and you can easily find your argument or the angle in this case. Alright, so let's work with an example. Okay, in this example, what I have done is I have an image of the circuit that I connected here, presented with the resistor and the capacitor right on the breadboard. Okay, so you see that I have a resistor. I connect it in a series with the capacitor. Okay, and this is the image, and this is the circuit diagram for this particular circuit. So given R equal to 270 ohms, capacitor equal to 1 microfarad, and the frequency is generated at 1 kilohertz. So how do we calculate the impedance in this case? And we have to write it in both rectangular and polar form. Okay, don't forget that I try to write all my numbers, all my values here as in 3 significant digits, because the expectation is that we will write our impedance both in rectangular and polar forms in 3 significant digits. Okay, so the solution is, because I have an RC circuit, I need to calculate my capacitive reactance using the formula 1 divided by 2 times pi times frequency times the capacitor. So key in all the values into your calculator. I have the capacitive reactance equal to 159 ohms. Expressed impedance in rectangular form will be equal to the real part, which is the value for your resistor, equal to 270 minus 159J ohms. So why do we put a minus in this case? Because the capacitive reactance will take on the negative part of J. Alright, okay. You can use calculator to easily convert this complex impedance into a polar form. So when I use my calculator, I have the modulus as 313 and the argument as negative 30.5 degrees. Okay, so again, they both represented with 3 significant digits. So let's move on to the next example. Again, okay, so I show you an image right here. The image that on the breadboard where I connect a resistor with a inductor, with an inductor in this case. So they are connected in series. Given again, R will be equal to 270 ohms. The inductor is 95.7 millihenries, and the frequency generated at this AC source is equal to 1 kilohertz. So from this, I can calculate the inductive reactance using the formulas 2 times pi times the frequency generated at the source and the value of my inductor as 95.7 millihenry. So plug this into your calculator using your engineering notation. Show the kilo here, the milli here. I have the answer as 601 ohms. Okay, express the impedance in rectangular form. Again, the real part of this impedance as complex number could be equal to your resistor, which is 270 ohms, and I add that with 601J. Why is it a positive here? Because according to the mathematical model, the inductive reactance will take on the positive part of J. Alright. Okay. Now, it's very simple for you to convert from rectangular form to polar form. So just a simple few keys on your calculator, you can convert this rectangular form into polar form, and you should review that And we did that in previous lesson, and I should have the answer as 659, and the angle equals to 65.8 degrees. And note that they all measure and round to 3 significant digits.